y por las dudas lo voy a grabar, ¿ok? Después
Sí.
vemos. Empezamos entonces.
Sí, sí, dale. Bueno, buenas tardes a todos. Gracias por la extrema paciencia que nos tuvieron. Tuvimos muchísimos problemas técnicos. Muchas gracias también a vos por esperarnos. El día de hoy tenemos el coloquio de Steve Nesbitt que nos va a hablar sobre convective storm initiation and mold near the Sierras de Córdoba en Argentina. Steven es profesor asociado del Departamento de Ciencias Atmosféricas de la Universidad de Illinois desde 2006. Su formación es en meteorología, habiendo estudiado en la Universidad Estatal de Nueva York, en la Universidad de Texas, hizo su doctorado en la Universidad de Utah. Los dejo con él para no perder más tiempo. Muchas gracias a todos por venir.
Muchas gracias y gracias a todos para la invitación del tiempo. I'm going to switch to English, but I will try to go slowly and I will give a somewhat compressed version given the time. But I'm really glad to be here today and want to thank especially Paula for her support over the years. We have recently compiled some information about our campaign, and we realize that we've been doing this for 10 years now. And I worked here for a semester in 2015, some of you may remember, and really got going on developing the project that became Relámpago Cacti. So thanks to everyone here and also all the students and staff members that helped with Relámpago. We couldn't do the project without you as well. So finally, let's acknowledge the funding from the agencies and especially here the Servicio Meteorológico Nacional and Nesbitt in Argentina who helped with the project. So today, most of you understand where the Sierra Córdoba here are. I don't need to explain this to you, like in the United States, but we focus primarily in the region of Central Argentina and today. I'll be talking about results really inspired by observations, but doing some numerical modeling of the convection that within this region, because we've garnered a lot of observational statistics, and now we can use models to help understand the dynamics of the forcing for the convection and also why it behaves in a certain way. So today's talk will be using the observations we collected to inspire some model results, looking at how the storms behave. So here's a picture of a thunderstorm. And up to this point, of course, thunderstorms are very complicated animals. We know that. And their behavior really oftentimes eludes models, and they're hard to predict. So one of the main objectives of Relámpago was to try to understand, in general, the behavior of thunderstorm initiation and propagation and growth. So today I'll be talking about these physical processes, and specifically I'll be talking a lot about a few quantities. One of them will be updraft width, basically what is the width of the cloud base or in the mid-levels of the air going up. What is the width of a downdraft and the air coming down? And how do the dynamic processes that occur within those through the change of phase of hydrometeors impact one thing that we know is very important in thunderstorm organization and development, a cold pool. So we will looking at these things in detail, and today's talk in specific terms, we'll be looking at a few questions. So first, what processes control convective initiation within the Sierras de Córdoba? And then what I call morphology, or essentially the evolution of the storms whether they be thunderstorms that develop into supercells or mesoscale convective systems. These are two types of organized. Skipping down, once initiation concern occurs, what will the storm mode be? And this is an important question for forecasters. It's also important for climate because thunderstorm organization is how upper level clouds develop and how thunderstorms impact the climate through changing the planetary albedo and by changing the water cycle. So we want to understand those key questions as it relates to storms within the region of the Sierras de Cordoba. And so basically, using all the Relámpago data, what combination of observations and models can we use to examine the concept of how it's organized within this we have affection in the Sierra de Cordoba. So I can spend another day exploring all the observations that we collect. And within the Sierras, we have idealized two-dimensional mountain barrier, or as about as idealized as you can possibly get on Earth, where we have the juxtaposition of strong upper-level flow in the mid-latitude jet stream, strong low-level flow in the southern low-level jet, and the mesoscale dynamics of the Sierra themselves, with their diurnal upscale, diurnal upslope and downslope flows that all combined into a very interesting, if you were to say Spanish, okay? It's a machine, okay? It's one of the most convective places on Earth. And so it's a good place for us to study how all these processes together. So we deployed mobile radars, radiosondes, observatories, mobile observatories, including the University of Illinois Doppler on Wheels radars, to examine these systems. And we collected a ton of data that we have just begun taking. So we knew going into Relámpago, this is a special place. We knew nothing about this that was going on. So this was really what we unlocked with questions that was what are the mesoscale processes that go into making these transforming works. So during our 45-day IOP, during Relámpago and almost 6 months of cacti, we collected a mountain of statistics that if you go into the literature now, there are papers that describe a lot of the different characteristics of the storms and their environments. We're happy to report that so far we've got 55 peer-reviewed publications from the project already. So we're very happy about that, but we continue to unlock more and more. So to try to understand some of the observed characteristics of the storms in isolation, today I'm going to be talking about some what we call idealized modeling experiments. So these are where we take the rest of the world away and we model just around the mountains here in a domain that's about 1,000 by 1,000 kilometers. And we're just going to put the Sierras in the middle and see what happens when we modify the exterior conditions around the mountains. This is kind of like having a petri dish and doing a laboratory experiment where we can try to control for everything else, but only have the Sierras de Cordoba in the middle of our petri dish and see what storms grow off of the mountains, okay? So this is work that was done by my student, Tinderjot Singh, who's now a postdoc at Colorado State. But what we're going to do is explore the observable database to try to find what are the storm characteristics that seem to be associated with particular types of storms. And today I'm going to focus on storms that form in the afternoon in the absence of pre-existing storms. And this is a pretty common feature in the Sierras de Cordoba in the spring and summertime. What I'm showing here on the upper left is a climatology from 2 years of radar data collected at RMA1 in Cordoba showing the initiation locations of storms between 11 and 20 UTC during the daytime. And you can see they're very tightly tied to the topography. Okay. And they form mostly on the eastern slopes of the Sierras. And we'll go into why that is here in a minute. And if we further subset this into daytime, mountain, and when there's a low-level jet in existence, you further subclassify that into storms that really like to form near the highest terrain and just east of it on the Sierras. So we're going to study this type of storm because it's a pretty predominant part of the climatology in this region, and it produces a lot of the severe weather that is observed along the eastern side of the Sierras, including Córdoba Capital. So when a low-level jet is present, again, it really focuses the storms. And we want to understand what factors control this particular location as a hotspot. Why not on the northern tip? Why not on the west side? Why not on the south side? Okay, it's not obvious that that should be a location where there's a lot of, topographic lifting of a low-level jet, et cetera. So we want to understand why that particular location is important. If we look at nighttime CI, convective initiation in contrast, okay, that happens over a much broader area. So that's a different class that we hope to understand with future work. And the composite sounding of all of the cases that are shown in B looks like this. Okay, you can see there's plenty of convective instability. The hodograph, or the wind change with height, shows there's a lot of vertical shear. Hodograph is relatively straight, but very intense, meaning that normally you'd think about a splitting supercell type situation with that sort of hodograph. At least in the United States, that would be what we would expect looking at this particular sounding. But of course, whether that happens in Argentina is another question. So what we're going to do is we're going to do our idealized modeling experiment where we do the Sierras in the model, pick out everything else, so no influence of the Andes or any other topographic features. We're going to put the observed sounding that was collected by the Servicio Meteorológico Nacional in a special site in a town called Villa Maria del Rio Seco, which is at the northern tip of the Sierras, relatively undisturbed by the topography, but you can see the strong northerly low-level jet around 900 hectopascals and above. Up there is the V wind profile, and you can see the blue line is the observed wind. So very strong low-level jet in this case. And what we're going to do is we're going to do some experiments where we play God, and we're going to reduce the low-level jet in a consistent way. So between the surface and 2,200 meters or so, we're going to gradually reduce the low-level jet. Okay. So this particular case in observations produced a very strong supercell, and it dumped hail near Rio Tercero in Cordoba. So let's have a look at the factors that go into the initiation of these storms. Okay, and here's an idea of what a model domain looks like. We zoomed into the center, but you can see we've removed all the remaining topography, and the extension of this domain goes out broader so that we don't have any boundary effects on our model. And here's all the details of all the model. We have open radiative boundary conditions so that whatever comes in, that sort of disappears. Okay, but the sounding at the borders is held constant, but we turn on surface flux. So we initialize the model in the morning, and radiation and surface fluxes will heat the atmosphere and destabilize it, and allow the development of diurnal slope flows on the Sierras. So here is what the coming 3 hours into the simulation. This is the circulation intervals, and what we see is the flow, and this is at just above the surface, about 100 meters above the surface, following the terrain. you can see that the flow starts to split around the Sierras. And this is a couple hours into the simulation. This is averaged over an hour and a half period. You can see the convergence zone that develops over the eastern slopes of the Sierras. Okay, now if you swing a little bit, the terrain is the light contour, and the colors in red are the mass convergence at that particular location. So here you see that this convergence line sits east of the slopes. Okay, and we were surprised by this. We were like, why isn't the most convergence over the top of the Sierras? Because you would think in a lot of simulations where there's a bell-shaped mountain, the most convergence is right at the top, right? So this was intriguing to us, and it actually agrees with what we see in observations, which I'll show in a minute, okay? Now, playing God here a little bit, changing the strength of the low-level jet, we actually find that the location of the mass convergence changes as a function of altitude. Okay, so we ran an experiment. That's the control up in the top. We turned off the boundary winds. Here, just leaving the diurnal circulation to develop on its own. And the convergence zone is right at the top of the mountain, like we would expect with no flow. And as we increase the low-level jet, we see that this convergence zone picks up already. We have the low-level jet at only 20% of intensity, and then continue up to the strongest in the observed case. Okay, so the flow around the Sierras coupled with the diurnal upslope flows to create this zone of convergence right near the eastern slopes of the Sierras. So why does this happen? Why does the zone convergence get enhanced when you enhance the low-level jet? Well, what we calculated the surface perturbation pressure. Okay, so this is basically the pressure at the given time minus the initial pressure of the model. And what you see is that the color scale here is perturbation pressure in pascals. You see that a mesoscale low pressure develops with the controlled low-level jet to the east of the terrain. And this mesoscale low pressure system is enhanced relative to the pressure on the west side when the low-level jet is strongest. When you have no low-level jet, the pressure is pretty much the same on both sides of the terrain. And at 50%, you see it actually is starting to get pretty strong. But when you have the full low-level jet, you get a mesoscale high pressure over here and a low pressure over here. And what this tells us is that the interaction of the flow with the Sierras causes this asymmetric pressure response. And that's because you have more terrain and higher terrain on the eastern side than you do on the western side. Okay, so the flow with this particular sounding is responding to that blockage here on the eastern side, and that causes there to be a low mesoscale low pressure system that develops here. That causes a lot of mass conversions in this region, and it also moves the convergence zone east so that it's not sitting over the top of the Sierras. Okay. Now this has a couple of different implications. First of all, there's some previous literature about mountain convergence zones, and there's a paper by Robert Banta in 1984. He attributed this to the fact that you have a lot of westerly momentum coming over a mountain, and that kind of limits the upslope flows. Okay, but we don't see that here because if you look actually near the top of the mountain, there's not a lot of westerly flow pouring over the top of the mountain. Okay, the one reason why that doesn't happen in the Sierras is because there's a strong inversion typically around 3 kilometers. And when you have that inversion, it really limits the momentum transport downward. Right? We don't see a lot of downslope windstorms in Cordoba like we might in Colorado. And that's because there's typically a capping inversion that's caused by the Andes upstream that limits that downward transport of momentum. So we do not see, like in the Rockies, this spillover of momentum down into the east. And it's really the response to the three-dimensional mountain that matters here. Okay, so what are the results of this whole thing? We've known from observational studies from Relampago that soundings launched in this region have a lot more vertical wind shear than sound west side Sierras, and also even up in the city of Cordoba itself. Okay, so this mesoscale region of about 30 kilometers wide is a region where you have really strong vertical wind shear. Okay. Part of that wind shear is the result of that mesolow sitting east of the Sierra that's driving flow to the east, and that increases the shear vector, leading to this increase in vertical shear. And of course, severe storms love vertical wind shear. Also, the development of mesoscale convection loves vertical wind shear. So this region just to the east of the Sierras this is one reason why it's a fábrica de tormentas, is because if you are successful at initiating convection in this environment, it's going to be explosive, okay? And we saw this in observations in TRAP et al. 2020. We were able to observe this enhancement in shear during this case. Various radio sounds just become the strongest shear with just east of the Sierra, and it was all so model does do that. And of course, that has the consequence that the upsets that form this environment are going to be strengthened by strong vertical wind shear and enter the parameter space of a severe storm relatively quickly. What it also does is this circulation helps bring moisture and instability into this region to the east of the Sierras. Okay, so this is a control simulation. This is near surface mixing ratio. Okay, and you see that as the simulation progresses, this really moist air is driven to very relatively high altitudes along this convergence zone. So the air is converging right along that line, and this relatively high moisture is able to be transported up the slope, so that can help enhance convective initiation. When we turn off the low level jet, you can see the moisture is not able to make it to the high elevation. So you're not going to get initiation in this case. When we turned off winds above 2.5 kilometers, you might say, well, if the Bandt hypothesis is correct, maybe there's something about this upper level flow affecting things. Actually, this panel looks identical to this one. It's not the upper level flow doing this. And finally, when we modified the low level jet, we saw that it had pretty much a linear effect on increasing moisture in the low levels, although the strength of the low level jet does affect how far the air is caused by entrainment, by the air trying to go up and over the Sierra. It actually changes position. So here it's relatively far south. When we weaken the low level jet, it moves north, such that convection actually initiates further north. Okay. So what we think is that the low level jet is important not only for this moisture transport, but it could help explain where in the Sierras, whether it's up near Los Gigantes, near Villa Carlos Paz, or down further to the south, it might be controlled by the strength of this low level jet. So that was kind of an interesting finding. I won't go into too many details. Convective instability and are highly correlated, and so the distribution of moisture highly controls CAPE. The terrain influences enhances CAPE with a low level jet, and it also reduces the convective instability by lifting moisture to higher altitudes. And I'll do some analysis of the trajectories of the air going around the Sierras, and just to emphasize that when we have the stronger low-level jet here on top, the power Sierra vapor mixing ratio. So basically, it shows that the high Cape air is actually coming around the mountain at low elevations and is pushed up slope and down here is essentially where the storms initiate. In a weaker case, they initiate further north because the low-level jet essentially is not forcing the air with sufficient momentum to keep going south. It's able to take advantage of the diurnal upslope flows and converge further north. And I'm just going to keep going here. So the conclusions of this part are, we have the splitting of the northerly low-level jet, splitting into two branches. The western branch crosses the ridgeline and collides with the eastern branch in this convergence zone that forms east of the terrain. And you can see this in observations and satellite images of the model. The asymmetry of terrain here, with more terrain here on the eastern side, causes more blockage, and that leads to a mesolow, which causes there to be air trying to, pressure gradient force leading to the air to come to the eastern side, and that's what pushes the convergence zone to the east. Downward momentum transport does not seem to play a role. I didn't show, but there's not really any effective mountain waves, and the low-level jet strength seems to be correlated with the location of CI. And this factor of the eastern slopes being favored here, and the fact that you basically have moisture divergence on the north side and convergence on the south side, leads to the reason why you have a lot of storm initiation and observations in this particular area, because that's the quadrant that is favored. So it helps explain in our observations why that is an important region. So the second part here, we'll talk about once the storm formed, what we do in this environment. So a paper by Dave Mullen, that was co-authored by myself and Paola, looked at the environment of these storms, and he classified these storms into different types of events depending on their morphology. Were they supercells? Were they mesoscale systems? Were they sort of unorganized convection, or were they kind of discrete storms that were very isolated? And so again, in the observations, he found that where the blue dots here, where the storms like to form, and then this red area is where they tended to grow to be mesoscale systems. Okay, so this region, in addition to being where CI happens, the region where storms grow on average in 40 minutes to be these large convective systems that have a bunch of hazards like hail, heavy precipitation, and strong winds. So the question we wanted to ask is, in the same framework that we just showed, what role does the low-level jet play in this? And can we use our idealized modeling framework to try to understand whether storms turn into supercells or upscale grow into MCSs? Okay. So we're going to look at, I'm just going to show you two case studies here, contrasting two storms that happened during the lava. Okay, so the top panel shows actually the case that I did previously, so 10 November. This is a storm that formed on an outflow boundary and quickly grew into a supercell. You can see that right here. I'm going to contrast that with storm on January 25th, which I think this sort of happened 3 or 4 times during Hecate, where we had supercells that developed high in the terrain, and then they grew upscale into a linear mesoscale convective system. Now, if we look at the observed wind profiles here for these two cases, we see that the 10 November case had a very strong low-level jet, and this was one of the strongest ones that we observed during the whole period. Whereas the January 25th case had a relatively weak northerly low-level jet. And so what we wanted to do is try to contrast what happens if you have the same environment, which these two cases had a pretty similar environment. The storms ended up being just as tall as each other. What happens when you control this low-level jet, and what happens to the storms following that evolution? So We did the same sound that we did in the previous one, January 25th case is quite similar. With a little bit moist, but we tested the sensitivity to that and it didn't really change the results that much. But what we did is we did a similar thing. We lowered the strength of low-level jet and kept all the same parameters of the study that we did before with the same model configuration. So basically, watch storm develop after they initiate. We're going to keep a lot of statistics about the storms. We're going to have the storms through life cycle. We're going to measure things like the area of the updraft, max vertical velocity. I'm not showing all these things, but we have further analysis that shows how all things are related. But we also measured called cold pool, because the cold pool gets strong and gets large, it's going to help that storm go into a linear system. Okay, so we're going to contrast the size of those things to our tracking, and I'll show you the statistical results with these different simulations. So to start off here, here's how storms evolved with these different low-level jet parameters. Okay? The strongest low-level jet is here. And then as we weaken it, you see it starts to get bigger. All more northerly instead of to the east. Okay? And this simulation actually looks like our 10 November supercell that formed and moved east. As we weaken the level jet, the storm starts to become more linear and look a lot more like the January 25th case, which formed into a line. So the nice thing about a model, of course, is that we can query the model for all of the parameters and the dynamics that resulted in this very different evolution. So when we track the strongest updraft bearing cell, these are the tracks of the storms we modified the low-level jet. Okay? And you can see a systematic evolution to the storm propagating more perpendicular, parallel to the terrain. 50% low jet case was the strongest, the largest. It also had the longest track. But overall, there was a systematic change in the direction of propagation. There were strong changes in the internal dynamics of the cells as well. The maximum vertical velocity, okay, actually got stronger with weaker low-level jet. Okay, that might be a little counterintuitive. Why would that be the case? Okay. The height of maximum vertical velocity increased with a weaker low-level jet. The area of the updraft of the strongest cell also increased. Area of the rain shaft increased. The cold pools got stronger, and the area of the cold pools got bigger. Okay. So what this is telling us is that these storms with a weaker low-level jet actually have stronger updrafts despite weaker low-level shear. And the cold pools and things that promote convective organization also become stronger. Okay, so that kind of agrees with some of the evolution that we've seen, including here's here in terms of temperature depth. That's shown. Here's a horizontal map and a vertical. The 50% case and the 75% case, and you can see that the strong updraft and downdraft started to produce massive cold pools in the 50% case. And that massive cold pool ended up leading to a long area of lift that helped lead to that mesoscale system. Whereas the weaker cold pools, they tended to remain more discrete because the cold pools were weaker. Now, in terms of the convective environments of these cells, it turns out they're not that different. Okay, and actually, 100% case had the strongest case. But it did not have the strongest updrafts or the widest updrafts. Okay? So it's kind of interesting. So we'll talk about more about that in a minute. The sin was very similar, and the shear was also very similar. So what's going on? Well, there are several factors that can change the storm motion. And the storm motion here really what's controlling the ability of the updrafts to be lifting unstable air. Okay, but basically going into the low-level jet instead of perpendicular. But there's some literature that shows what are some factors that could affect supercell motion. Right? Of course, one is storm advection. Second one is propagation due to dynamic vertical pressure perturbation forcing, okay, or nonlinear pressure forcing. Okay, these are interactions between the updraft and the vertical wind shear. That if you go into the supercell literature, you will find that this is why supercells tend to propagate deviant to the wind and also tend to split. Okay, so that is an important factor. The third one, of course, is gust front lifting, because gust fronts can also lead to updrafts. But in most supercell analyses, that's ignored. Okay. And then number 4 is miscellaneous factors, such as complex terrain. That's not a factor because when these storms are off the Sierras, they're not in that complex of terrain. So we find that the 3% case is most relative to. So that deviation we think is important for the ability of the cold pool to lift air into that updraft. Okay, and looking at the mean V wind, okay, there's not really much change here. Maybe a few meters per second. That doesn't explain the storm being affected very long distances like we see in the simulation. We see the updraft helicity is the strongest, which would be sort of related to the spin term of the nonlinear pressure perturbation force. Storm relative helicity is actually strongest in the 100% low-level jet case, which would cause that to be more deviant, but it's not. So that's confusing to us. And the storm relative flow, which has been argued to be important for updraft strength, is the same for all these cases. So what's going on here? We take a look at photograph analysis, and what we find is that the observed storm motion, which is the star, which is in the strongest low-level jet case, is basically much weaker in terms of its northerly motion than in the weakest low-level jet case. We find that when we look at the analysis of the bunker storm motion, which takes into account the storm relative flow for splitting supercells, sort of agrees with these things, but it's definitely about 8 meters per second too weak compared to the observed cell. So something else is causing that to happen, and that what we think is the gust motion. We did an analysis of the pressure terms for these forcings for the updraft. Okay, so up on the upper left is linear dynamic vertical pressure perturbation forcing. Okay, this is basically updrafts are favored on their downshear side to form new updrafts. We have the nonlinear perturbation force, which has to do with the vertical vorticity that causes the storms to split. And then we're going to also show the low-level mass convergence as gust front forcing for new vertical motion. And when we examine we see a classic supercell situation here. When we look at these different terms for the forcing, the red and pink here are the linear and nonlinear terms respectively. Okay, we see that the storm basically is favored on the downshear side. There's not a lot of verticality, so it's basically just linear forcing making this go with the low-level wind. The gust front forcing here is on the rear flank of the storm, and it turns out all updrafts actually form that, which is typical of an isolated supercell. So in this case, that storm stays as a supercell, propagates normally away from the terrain. But let's contrast that with our weaker low level jets. The blue one is cold pool, 1.5 degrees Kelvin. And when we see our updraft form, we see it's much wider. And we'll see the gust front extends all the way along this region. It's much hotter. And the updraft just follows that gust front force. Okay. The linear and non-pressure forcing is on the eastern side, which is trying to have the solar off the east, but the gust front force just keeps pulling it north. Okay, so completely these are different dynamic forcing mechanisms, which you expect for sort of hybrid supercell situation, and whereas this is more of your classic supercell. So if we look at carefully at options for the addition from this gust front simulation to the supercell-like simulation, and what it does is it recontrols how the cells grow and propagate. So based on analysis of the environmental sound, it might be possible to help predict these things like which understand how dust fronts might propagate. But just to start off here, with a strong low net, we see that which is the red and the blue. They're mainly forced by linear pressure forcing terms, and the storm propagates slightly to the 0 to 6 kilometer. For the weaker level jet, we see that this gust front forcing combines with these forcing terms, and the storm propagates off to the northeast with a stronger cold pool. So very different evolution, which helps us understand that for similar sort of thermodynamic environments, the low-level jet may be a key control on how these storms eventually leave the Sierras. So to conclude, in the storms in the weaker low-level jet environments, like we see typically in the summertime in the Sierras, are likely to have, based on our sort of theory here, a stronger component of motion perpendicular to the ridge of the Sierras de Cordoba. They produce intense and wider updrafts, which we see on satellite, and they have stronger cold pools compared to the stronger low-level jet storms. We looked at the updraft forcing, and that shows that there's a larger and stronger cold pools produced by weaker low-level jet storms, and that seems to control the motion to a higher degree. And the weaker low-level jet environments are more likely to produce the terrain cold pool dominant storms, and more likely to produce a mesoscale convective system. So those are two aspects of Relampico that I've described today, but we're continuing to analyze this extensive and collaborate many people here in doing so, and we want to continue the legacy of capacity building together across the divide of North and South America to help improve understanding of severe weather globally. And you know, Paula and I have dreams. Maybe someday there'll be a Relampico 2, where we can come back and focus on different aspects to help understand how convection behaves here in not only just the Sierras de Cordoba, but other regions of South America. And with that, I will thank you. I'll take questions if you'd like to ask in Spanish. I'll try to respond to you.
I'm going to start sharing, so people also in Zoom can ask questions. Y si alguien tiene preguntas, o si alguien, por favor, si alguien tiene una pregunta, escuchamos. Ahí se ajusta a mí para preguntar.
question. When you decided the strategy for the simulation, you consider only the change in the low level check only. Then the environment is fixed. You have a cave condition, and when you see the change, is the change from the beginning of the simulation.
Yeah.
For example, difference in cave, you need strong low level jet or 50% low level jet.
Yeah, so we ran the simulation with the January 25 thermodynamics. We probably saw more convection develop, but the mechanisms were very similar. There was so much in the sounding from January 25th that we just saw explosive development everywhere, but we did tend to see differences in the storm propagation that were similar to this.
Okay, but in general, when we have this strong difference with the low level jet, we also have difference in the environment. Because, we cannot fix the environment under these conditions.
Right.
Are you planning to do the same, fix the low level jet and starting with a different type of thermodynamics? Maybe you did it already.
Yeah, well,
It was just a problem of initiation or?
Yeah, so this sounding was borderline in terms of initiating anything.
Okay.
Right, if we go any drier,
No.
you're not going to get anything.
Nothing will happen.
And like I think I mentioned it with the moisture sounding, we get a lot of convection that develops, and I think that's probably because in a real simulation, there's probably large scale subsidence that's happening over time.
Yeah, because you turn it on off the Yandex.
Right. Right. So that might be one reason why when we increase the moisture, we just get a lot of convection. So it's, these sort of controlled experiments, you can only do so much, but it might be interesting to try to, because we can turn on large scale subsidence and see if we get something more realistic with other environments. But that's a good point.
¿Alguna otra pregunta? No me puedo comunicar con Julia, no sé si nos están escuchando.
Sí, estamos.
I have a question. I think it's an easy one. You said that there is something different in Córdoba than from northern. I think you said about the Rocky Mountains with that momentum downdraft. Do you think that's because of the height of the, or there is any other factor?
Yeah, it's a good question. So, I mean, in the compare, the Rocky Mountains, right? We're up at, let's say, 4 kilometers, and the plains around those Rocky Mountains are at 2 kilometers, right? So, there's not really any capping inversion that sits over the mountains. I mean, if you launch a sounding up there, there's a lot. You're basically the PBL is heavily influenced by the free atmosphere, and there's no temperature inversion to help protect that. That's significant. So there's a lot of dry convection going on too. Whereas in the Sierras de Cordoba, like I mentioned, there's due to the Andes, and you have downslope flow, and that produces a very strong, very stable layer that the convection has to break through. And the only place it can do that is where the Sierras de Cordoba start to erode that capping inversion due to mixing and so forth, right? We don't observe a lot of convective initiation over here because you're just sitting under the stacking inversion. So I think that the mountains, the Sierras de Cordoba are really important for the whole hydrology of central Argentina, because it's the place where the geography sets the stage where you can break this inversion and then the clouds can propagate this way. Also, synoptic forcing is an important factor as well. But that's what's different up here in the high Rockies. I mean, the momentum that's westerly is, there's nothing keeping it from coming down, and you have a lot of downslope windstorms. So, yeah.
Any other questions?
No questions in the
I
chat.
don't think much. Thank you, Steve, again. Gracias. Gracias a todos por venir. La semana que viene, como les decía al principio, tenemos 2 coloquios, uno el jueves y uno el viernes.